Tonight, we're going to look into the mouth of the universe's darkest secret. Not metaphorically, not poetically, literally. A telescope the size of a tennis court, floating 1,000,000 miles from Earth in the silence of deep space, aimed itself at one of the most violent and impossible objects in all of existence, a black hole billions of times more massive than our Sun. And it looked, really looked, with instruments so precise they can detect the heat of a single candle flame from the distance of the Moon. And what it found broke something. Not just a model, not just an equation, something deeper, something physicists had trusted for over a century without question, something that was supposed to be unbreakable. Here is what makes this so terrifying. Black holes were always supposed to be the place where our questions stop, where the laws of physics hit a wall, where even light surrenders. Scientists had accepted that. They had made peace with the idea that some things simply cannot be known, cannot be measured, cannot be seen. And then we built the James Webb Space Telescope, and we looked anyway, and the universe answered. And the answer was not what anyone expected. The answer was not supposed to be possible. The data came back, and the scientists went quiet, because the numbers on the screen described something that, according to everything we know, should not exist. By the end of tonight, you're going to understand exactly why what James Webb saw has shaken the foundations of modern physics, what it means for our understanding of space, time, and reality itself, and why this single observation may be the beginning of the most profound scientific revolution since Einstein sat in a patent office and reimagined the nature of gravity. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. There is a place in the universe where everything ends. Not ends the way a road ends, or the way a story ends, or even the way a life ends. It ends the way mathematics ends, the way logic ends, the way the very concept of place and time ceases to have any meaning at all. Scientists have a name for it. They call it a singularity. And for most of human history, we assumed we would never be able to see it. We assumed it was beyond us, hidden behind a veil so absolute, so final, that no instrument we could ever build would be capable of pulling back even a corner of it. That assumption held for a long time. For decades, black holes existed mostly as theoretical objects, creatures of equations born in the mathematics of Einstein's general relativity and grown into monsters in the imaginations of physicists who spent their careers describing things they believed could never be directly observed. They were real? Yes. We had evidence of them. We had seen their influence on the stars around them, the way they bent light, the way they pulled gas and dust into spiraling storms of unimaginable energy. We had even captured the first blurry image of one in the year 2019, a feat that took over 200 scientists and enough data to fill 1/2 ton of hard drives. But seeing the shadow of something is not the same as looking into it. Knowing something exists is not the same as understanding what it does. And then came Webb, the James Webb Space Telescope, launched on Christmas Day of 2021 after more than 2 decades of engineering, delays, and a budget that grew to nearly $10 billion. A machine so sensitive, so precise, so fundamentally different from anything we had ever sent into space that astronomers immediately began pointing it at things they had previously considered too difficult, too dark, too far, or too impossible to observe with any clarity. Webb sees in infrared light, the kind of light our eyes cannot detect, the kind of light that passes through dust clouds that would blind any ordinary telescope, the kind of light that carries information from the earliest moments of the universe. With Webb, we could suddenly see things that had been invisible to us for our entire history as a species. So we pointed it at a black hole. Of course we did. We aimed the most powerful space telescope humanity has ever constructed at the most extreme object in the known universe, and we let it look. And what came back? The data, the measurements, the light curves and spectral signatures that Webb's instruments recorded and transmitted back across 1 million miles of empty space to the teams of scientists waiting on the ground, was not what anyone had predicted. It was not an anomaly that could be explained away with a recalibration or a software update. It was not noise or interference or a technical artifact of the observation. It was a signal, a clear, undeniable, repeatable signal. And that signal described something that, according to the laws of physics, as we currently understand them, should be impossible. That word gets used too easily in science, impossible. Most of the time, when scientists say something seems impossible, they mean it is unlikely or unexpected or inconsistent with one particular model. But this is different. What Webb observed near the event horizon of a supermassive black hole at the center of a distant galaxy contradicts not one model, not one theory, but two of the most tested, most verified, most reliable frameworks in all of modern physics simultaneously. It sits at the exact intersection where general relativity and quantum mechanics meet and violently disagree. And that disagreement, which physicists have known about for decades as a theoretical problem, has now produced something that can be measured, something that shows up in real data, something that is sitting in spreadsheets and research papers right now, as you listen to these words, being debated by some of the most brilliant minds on Earth. I want you to feel the weight of that for a moment. Think about what physics has given us. The equations that describe gravity and the curvature of space-time have guided spacecraft to the outer edges of our solar system with accuracy measured in kilometers across billions of miles of emptiness. The quantum mechanical principles that describe the behavior of particles at the smallest scales have given us transistors, lasers, and every piece of technology you interact with in your daily life. These are not rough approximations. These are not working theories in the casual sense. They are among the most precisely tested ideas in the entire history of human thought. And Webb found something that neither of them can fully explain. That is where we are tonight, at the edge of what we know, standing at the boundary between the familiar and the genuinely, profoundly unknown. And I think it is worth taking a moment, before we go any further, to appreciate how extraordinary that is. In human history, there have been only a handful of moments when a single observation forced an entire scientific civilization to reconsider its deepest assumptions. When Galileo pointed his telescope at Jupiter and watched moons orbit another planet, he did not just see new objects in the sky. He broke a world view. When Arthur Eddington measured the bending of starlight during a solar eclipse in 1919, he did not just confirm a prediction. He replaced the Newtonian universe with an Einsteinian one. We may be living through one of those moments right now, a moment when the universe has shown us something we cannot explain. And the only honest response is to lean in, to look harder, and to admit with humility and with wonder that we do not yet understand what we are seeing. So tonight, we go to the edge. We follow the light that Webb collected across the incomprehensible darkness of intergalactic space. We sit with the numbers that broke the equations. We listen to the silence that fell over the teams of scientists when the data first came through. And we ask the question that has always driven human beings forward. Across every ocean, through every unknown, into every shadow we were afraid of. What is actually there? What is really happening in the place where space ends and something else begins? The universe has been keeping this secret for 13.8 billion years. James Webb just got the first real look, and what it saw has changed everything. Before we can understand what Webb saw, we need to understand what a black hole actually is. Not the Hollywood version, not the swirling purple vortex with a dramatic soundtrack. The real thing. Because the real thing is, if anything, far stranger and far more unsettling than anything a film could show you. And the strange part is not the darkness or the gravity or even the destruction. The strange part is what a black hole tells us about the nature of space and time themselves. That is where the real mystery lives, and that is where we need to start. Let me give you the simplest possible version first. A black hole is a region of space where gravity is so extreme that nothing, not matter, not energy, not light itself, can escape once it crosses a certain boundary. That boundary has a name. We call it the event horizon. Think of it like this. Imagine you're standing beside a river, and the river is flowing toward a waterfall. Far from the waterfall, the current is gentle. You could swim against it if you wanted to. You have options. You have freedom of movement. But as you get closer to the edge, the current gets faster, and at some point, you reach a place where the water is moving faster than you can possibly swim. It does not matter how strong you are. It does not matter how hard you try. The current will take you. That point of no return is the event horizon. And in the case of a black hole, the current is gravity, and the waterfall is a place where our understanding of physics completely breaks down. Now here is the thing most people do not realize about event horizons. If you were falling toward one, you would not see a wall. You would not feel a sudden jolt or hear an alarm. The event horizon is not a physical surface. It is not made of anything. It is simply a location in space, a mathematical boundary, where the escape velocity equals the speed of light. Escape velocity is the speed you need to reach to pull yourself free from a gravitational field. On Earth, that is roughly 11 kilometers per second. That is why rockets need to travel so fast to reach orbit. At the event horizon of a black hole, that escape velocity reaches 300,000 kilometers per second. The speed of light, which is the fastest anything in the universe can travel. Cross that line and you cannot get out. Not because something stops you, but because the geometry of space itself is pulling you inward faster than anything can move outward. You are not trapped. You are simply in a place where every direction, including what used to be up, now leads deeper in. So where do black holes come from? The most common kind, the kind we talk about when we discuss stellar black holes, are born from the death of massive stars. When a star many times larger than our Sun exhausts its nuclear fuel, the outward pressure that had been balancing gravity for millions of years suddenly disappears. The core collapses. In a fraction of a second, a ball of gas millions of kilometers wide implodes into a point smaller than an atom. The outer layers of the star rebound in a catastrophic explosion we call a supernova, one of the most energetic events in the known universe. And what remains at the center, if the original star was massive enough, is a black hole, a point of such extraordinary density that the space-time around it is permanently, irreversibly curved inward. A wound in the fabric of the cosmos that does not heal. But the black holes we are most interested in tonight are not stellar black holes. They are something far larger and far more mysterious, supermassive black holes. These are the colossal engines that sit at the centers of almost every large galaxy in the universe, including our own Milky Way. Our central black hole, known as Sagittarius A star, has a mass of roughly 4 million times that of our Sun. 4 million solar masses, compressed into a region smaller than our solar system. And Sagittarius A star is considered modest by comparison to some of the giants we have found elsewhere. The black hole that Webb observed has a mass billions of times greater than our Sun. Billions. A gravitational influence stretching across distances that dwarf the entire span of our galaxy. We do not fully understand how supermassive black holes got so large. That is another unsolved mystery. But they are there, at the heart of nearly every galaxy, quietly governing the motion of hundreds of billions of stars. Now I want you to sit with the concept of the singularity for a moment, because this is where things get genuinely strange. At the center of a black hole, according to our best equations, all the mass that created it is compressed into a single point of zero volume and infinite density. a singularity. Infinite density means the curvature of space-time becomes infinite. And when something in your equations becomes infinite, it is not a result. It is a warning. It means your equations have broken. It means you're trying to describe something that your mathematical framework was not built to handle. Physicists call this a breakdown of the theory. And general relativity, Einstein's gorgeous century-old description of gravity, breaks down completely at the singularity. It simply cannot tell you what is there. The math stops working. The pencil falls off the page. And that silence at the center of the equation is one of the deepest unsolved problems in all of science. Here is something that might help you feel the scale of what we are dealing with. If you took our Sun, a star 1,300,000 times the volume of Earth, and compressed it until it became a black hole, the resulting object would be roughly 3 kilometers across. 3 kilometers, the same distance you might walk to a neighborhood coffee shop on a weekend morning. That is how densely packed a black hole is. That is how extreme the physics becomes. Now multiply that by 4 million for our galactic center. Multiply it by billions for the monsters Webb is studying. The numbers stop feeling like numbers, they start feeling like the universe is trying to tell you something. That reality has corners we have not looked into yet. That there are places where the rules we trust, the rules we built our entire technological civilization on, simply do not apply. And that is exactly what makes what Webb found so significant. Because Webb did not just observe a black hole from a safe, comfortable distance. It looked closer than anything before it. It captured light and radiation from the region just outside the event horizon, the most extreme environment our instruments have ever studied. And what that light carried back to us, encoded in its wavelengths and frequencies and intensities, was a message. A message that said, the story you have been telling about this place is not quite right. Something is happening here that your equations did not predict. Something is happening here that changes what we thought we knew. And tonight, slowly and quietly, we are going to figure out what that something is. To understand why Webb changed everything, you need to understand what Webb actually is. Not in the technical sense, not the specifications and the engineering diagrams and the wavelength ranges. In the human sense, because the James Webb Space Telescope is not just a piece of hardware, it is the result of more than 20 years of work by thousands of scientists, engineers, and technicians across 14 countries. It is the product of arguments and revisions and near cancellations and breakthroughs that stretched across the careers of an entire generation of astronomers. It is, by almost any measure, the most complex scientific instrument humanity has ever successfully deployed. And when it finally opened its golden eye in the depths of space, the universe began showing us things it had kept hidden for billions of years. Let me tell you what makes Webb fundamentally different from every telescope that came before it. The answer comes down to a single concept: the kind of light it sees. Ordinary telescopes, including the Hubble Space Telescope, which gave us some of the most iconic images in the history of astronomy, operate primarily in visible light, the same light your eyes can detect, the same narrow slice of the electromagnetic spectrum that evolution equipped us to perceive. Visible light is extraordinary. It has revealed galaxies, nebulae, and the expanding structure of the cosmos. But visible light has a problem. It gets blocked. Dust clouds absorb it. Cosmic expansion stretches it. Ancient light from the earliest galaxies has been traveling for so long that by the time it reaches us, it has shifted completely out of the visible range and into something our eyes cannot see at all. Webb was built to see that something: infrared light, the light of the deep past, the light that carries the oldest secrets. Infrared light is essentially heat radiation. Everything that has any temperature at all emits it, including you, sitting or lying wherever you are right now, radiating warmth into the darkness around you. The universe emits it too. in vast ancient waves that have been travelling since long before our sun was born. Webb's mirrors and detectors are tuned to capture this infrared signal with a precision that was, until recently, considered technically impossible to achieve in space. The primary mirror alone, that famous golden honeycomb of 18 hexagonal segments, spans 6.5 meters across. Compare that to Hubble's 2.4 meter mirror, and you begin to understand the difference in sensitivity. Webb collects more than 6 times as much light as Hubble. In practical terms, that means it can see objects roughly 100 times fainter, objects that were, for all of human history, simply invisible. But raw mirror size is only part of the story. Where Webb operates matters just as much as what it is made of. Hubble orbits Earth at roughly 550 kilometers above the surface, close enough that astronauts could visit it for repairs and upgrades. Webb does not orbit Earth. It sits at a point in space called the second Lagrange point, or L2, approximately 1,500,000 kilometers from our planet in the direction away from the Sun. At that distance, Earth's gravity and the Sun's gravity balance each other in a way that allows Webb to maintain a stable position while orbiting the Sun in lockstep with our planet. 1,500,000 kilometers. To put that in perspective, the Moon is roughly 380,000 kilometers away. Webb is nearly 4 times farther from Earth than the Moon. If something went wrong with it tomorrow, no astronaut could reach it. No repair mission could save it. It is entirely on its own out there, in the cold and the silence, doing its work alone. And it must stay cold. This is one of the most remarkable engineering challenges the Webb team had to solve. Infrared detectors are extraordinarily sensitive to heat, including the heat of the telescope itself. If Webb's mirrors and instruments were at room temperature, they would glow in infrared so brightly that the light from distant galaxies would be completely drowned out, like trying to see a candle flame from across a field while someone shines a floodlight in your eyes. To prevent this, Webb was equipped with a sun shield, a 5-layered, tennis court-sized membrane made of a material called Kapton, coated in aluminum and silicon. That sun shield blocks the heat and light of the Sun, the Earth, and the Moon simultaneously, keeping Webb's instruments at a temperature of around -233 degrees Celsius. That is just 40 degrees above absolute zero, the coldest possible temperature in the universe. Webb operates in a cold so profound it makes the surface of Pluto feel warm by comparison. The telescope launched on the 25th of December 2021 atop an Ariane 5 rocket from the Guiana Space Center in South America. The launch was, by the standards of what followed, the easy part. What came next was a month-long deployment sequence so complex and so unforgiving that engineers referred to it privately as the most stressful 30 days in the history of space science. Webb had to unfold itself in deep space. The sun shield alone required over 300 single-point failure mechanisms to deploy correctly, meaning 300 separate steps where a single malfunction would have ended the mission permanently. The primary mirror had to unfold segment by segment. The secondary mirror had to extend on a tripod of booms. Every hinge, every latch, every motor had to work perfectly, in sequence, in the vacuum and radiation of deep space, with no possibility of human intervention. They all did. On the 14th of January, 2022, the last mirror segment locked into place, and Webb was whole. The first full-colour images were released to the public on the 12th of July, 2022. When they appeared on screens around the world, many people, including scientists who had spent decades building the instrument, cried. Not because the pictures were pretty, though they were extraordinary, but because of what they represented. One of the images showed a cluster of galaxies so massive that its combined gravity bent the space-time around it, creating natural lenses that magnified the light of galaxies far behind it, galaxies so distant that their light had been travelling for more than 13 billion years before reaching Webb's mirror. 13 billion years. The universe is 13.8 billion years old. Webb was seeing light that left its source when the cosmos was less than a billion years old. We were looking at the infancy of everything. And then the teams began pointing Webb at the things that had always been most mysterious, the things that had always sat at the boundary of what we could observe and what we could only theorize about. Black holes, the hearts of distant galaxies, the regions of space where gravity becomes so extreme that the normal rules dissolve. They pointed Webb at these places because Webb, unlike anything before it, had a genuine chance of seeing something real, something measurable, something that could either confirm what our equations predicted or reveal that our equations were missing something fundamental. As it turned out, it was the second one. And what Webb found in those regions of extreme gravity, what its instruments recorded in careful, patient, undeniable detail, is what brought us here tonight. Not all black holes are created equal. The ones born from dying stars, the stellar black holes we discussed earlier, are enormous by any human standard, but they are modest by the standards of the cosmos. A typical stellar black hole might contain 10, 20, perhaps 50 times the mass of our Sun, compressed into a sphere a few dozen kilometers across. Terrifying in their own right, but small, contained, local. The kind of black hole you could, in theory, study from a relatively safe distance without it dominating the entire structure of a galaxy around it. The black hole that Webb turned its golden mirror toward is nothing like that. It belongs to a different category entirely. A category so extreme that even the word massive feels inadequate. We are talking about a supermassive black hole, and the one at the center of our story is among the largest, most gravitationally dominant objects ever observed by human instruments. The galaxy in question lies billions of light years from Earth. Let that distance settle for a moment. 1 light year is the distance light travels in a single year, moving at 300,000 kilometers per second without stopping. 1 light year is roughly 9.5 trillion kilometers. Billions of light years means that the light Webb captured from this galaxy left its source when the universe was a fraction of its current age. It traveled across the expanding cosmos for an almost incomprehensible span of time, longer than Earth has existed, longer than our Sun has burned, before finally arriving at Webb's mirrors floating in the quiet dark beyond our moon. We are not looking at something that exists right now in the present moment. We are looking at something that existed in the deep past, a fossil of light, a message from an era when the universe was young and violent and still finding its shape. At the heart of this ancient galaxy sits a black hole with a mass estimated at several billion times that of our Sun. Billions of solar masses. To put that in some kind of human terms, consider this. Our Sun contains 99.8% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every particle of dust orbiting our star for billions of kilometers in every direction. All of it combined makes up just 0.2% of our solar system's total mass. The Sun is already an almost incomprehensible concentration of matter. Now multiply it by several billion. That is what sits at the center of the galaxy Webb was studying. A gravitational engine of such magnitude that its influence shapes the motion of hundreds of billions of stars across a region of space tens of thousands of light years wide. The entire galaxy, in a very real sense, revolves around it. Not metaphorically, literally. The black hole is the axis. Everything else is just orbiting the drain. Objects like this have a name beyond simply supermassive. When a black hole reaches this scale, billions of solar masses, actively consuming surrounding material and radiating energy across the electromagnetic spectrum, it powers what astronomers call an active galactic nucleus, or AGN, and the most luminous, most energetic version of an active galactic nucleus is something called a quasar. Quasars are among the brightest objects in the observable universe, A single quasar can outshine an entire galaxy of hundreds of billions of stars, all from a region of space no larger than our solar system. The energy comes from the accretion disk, a vast flattened structure of superheated gas and dust spiraling inward toward the event horizon at a significant fraction of the speed of light. As that material falls inward, it compresses and heats to temperatures of millions of degrees, radiating light across every wavelength from radio waves to X-rays. The black hole does not just sit there in silence, it screams. Across billions of light years, it screams in every frequency we know how to measure. But here is the thing most people do not realize about these monsters. For all their violence, for all their energy, for all the light they blast across the cosmos, there is a boundary beyond which we know almost nothing. The accretion disk is visible. The jets of plasma they sometimes fire perpendicular to the disk, stretching for thousands of light years into intergalactic space, are visible. The influence on surrounding stars is measurable, but the event horizon itself and what lies beyond it has always been beyond our reach, always been shrouded, always been the place where our data runs out and our theories take over, with nothing to check them against. Until Webb looked. Until Webb, with its extraordinary sensitivity to infrared light and its ability to resolve structures at scales and distances that no previous instrument could match, stared at the region just outside the event horizon of this billion solar mass engine and recorded what it found. What the accretion disk of a black hole this size looks like in practice is almost impossible to fully imagine. The gas and dust spiraling inward is not a gentle, orderly flow. It is a maelstrom, a disk of matter potentially hundreds of millions of kilometers across, spinning at velocities that approach a meaningful fraction of the speed of light at the innermost edge. The temperature at the outer edges of the disk is already tens of thousands of degrees, hotter than the surface of most stars. At the innermost stable orbit, just before matter crosses the point of no return, temperatures rise into the millions of degrees. The entire structure is threaded with magnetic fields of extraordinary strength, twisted and coiled by the rotation of the infalling material until they snap and reconnect in violent eruptions that launch jets of relativistic plasma outward along the black hole's rotational axis. This is not a quiet place. This is the most energetically extreme environment in the post-Big Bang universe. And this is exactly where Webb looked. The reason astronomers chose this particular target was not random. This galaxy and the supermassive black hole at its center had been observed before by other telescopes, in X-ray and radio, in visible light. There was already a body of data describing it, a baseline of measurements against which Webb's new observations could be compared. Scientists knew what our existing models predicted they should find when Webb added its infrared vision to the picture. They had calculations, they had simulations, they had decades of theoretical work describing how the space-time around a black hole of this mass should behave, how the light from the accretion disk should appear when seen through Webb's instruments, what signatures the interaction of matter and extreme gravity should produce. The predictions were specific, the models were confident, and when Webb's data finally arrived, when the scientists sat down with the numbers and began comparing what they had expected to see against what they had actually measured, the room went quiet. Because the numbers did not match. They did not match in a way that was small enough to dismiss. They did not match in a way that pointed to a calibration error or a background contaminant. They did not match in a way that anyone had a ready explanation for. The monster at the center of that distant galaxy had shown Webb something the equations had never predicted, and now, slowly, we're going to figure out what it was. Before we can appreciate what broke, we need to understand what was supposed to hold. We need to sit with the rules, the elegant, tested, magnificently reliable rules that physicists have spent over a century building, verifying, and trusting with their careers and their reputations, and, in a very real sense, with the entire technological infrastructure of modern civilization. Because the story of what Webb found near that black hole is not just a story about a surprising measurement, it is a story about two of the greatest intellectual achievements in human history colliding with each other in a place where neither one can fully survive. And to feel the weight of that collision, you first need to understand what each of them claims and why we believed them so completely. The first framework is general relativity. Albert Einstein published his general theory of relativity in November of 1915, and it remains, more than a century later, one of the most beautiful and most precisely confirmed theories in all of science. What Einstein proposed was a complete reimagining of what gravity actually is. Before Einstein, we followed Isaac Newton's description: gravity as a force, an invisible pull between masses, operating instantly across any distance. Newton's gravity worked extraordinarily well for most purposes. It predicted the motion of planets, the trajectories of cannonballs, the tides of the ocean, but it had cracks. It could not fully explain the precession of Mercury's orbit. It broke down at very high velocities, and it offered no explanation for how exactly one mass could reach across empty space and pull on another without any medium to carry the force. Einstein replaced all of that with something far more radical and far more profound. He said that gravity is not a force at all, it is the curvature of space-time. Space and time, he argued, are not separate and independent. They are woven together into a single four-dimensional fabric called space-time. And mass curves that fabric. Think of it like a heavy ball sitting on a stretched rubber sheet. The ball creates a depression, a curve in the surface. If you roll a smaller ball nearby, it does not get pulled by an invisible force. It simply follows the curved surface, and the curve guides it toward the heavier object. That is what gravity is, according to Einstein. Not a pull, a curve, a geometric property of the fabric of reality itself. And the more mass you concentrate in one place, the more extreme the curvature becomes. At the center of a black hole, where the mass is theoretically compressed to an infinitely small point, the curvature of space-time becomes infinite. The geometry of the universe itself breaks down. The equations produce a singularity. And as we discussed earlier, a singularity in your equations is not an answer. It is a confession that your theory has reached its limit. General relativity has been tested in ways that would have seemed miraculous to Einstein himself. We have measured the bending of light around the sun, precisely as the theory predicted during solar eclipses. We have detected the slowing of time in stronger gravitational fields. GPS satellites have to correct for this effect constantly, because time genuinely runs faster for them in their weaker gravitational environment than it does for us on the surface of Earth. And without that correction, your navigation app would accumulate errors of kilometers every single day. We have detected gravitational waves, ripples in the fabric of space-time itself, produced by colliding black holes and neutron stars, exactly as general relativity predicted they should exist and behave. In every test, in every environment we have been able to probe, general relativity has held perfectly, without exception. It is, by every measure we have, the correct description of gravity. The second framework is quantum mechanics, where general relativity describes the very large, planets, stars, galaxies, the curvature of space-time across cosmic distances. Quantum mechanics describes the very small, the behavior of particles at the subatomic scale, electrons, photons, quarks, the fundamental constituents of everything you have ever touched or seen or tasted. Quantum mechanics emerged in the early 20th century from the work of a constellation of brilliant minds: Planck, Bohr, Heisenberg, Schrödinger, Dirac, and it is, if anything, even more strange and counterintuitive than relativity. It describes a universe where particles do not have definite positions or velocities until they are measured, where a single particle can exist in multiple states simultaneously, where two particles can be entangled across any distance such that measuring one instantly affects what you find when you measure the other, where empty space is not actually empty, but seething with pairs of virtual particles constantly flickering in and out of existence. Quantum mechanics is not a speculative theory. It is the foundation of almost every technology you interact with in daily life. Transistors, the basic building blocks of every computer and smartphone and digital device, work because of quantum mechanical effects. Lasers work because of quantum mechanics. MRI machines, LED lights, solar panels, all of them depend on quantum mechanical principles for their operation. The theory has been tested to a precision that staggers the imagination. Certain predictions of quantum electrodynamics, the quantum theory of light and matter, have been verified experimentally to an accuracy of 1 part in a trillion. That is equivalent to measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. Quantum mechanics is not approximately right. It is right to a degree that borders on the philosophically unsettling. So here is the problem. Here is the crack at the foundation of everything. General relativity and quantum mechanics are both extraordinarily, impeccably, almost miraculously accurate descriptions of reality in their respective domains, but they are mathematically incompatible with each other. When you try to apply the principles of quantum mechanics to a region of extremely curved spacetime, like the interior of a black hole, the equations produce nonsensical results. Infinities appear where they should not. Probabilities come out greater than 100%, which is physically meaningless. The two frameworks simply do not speak the same mathematical language, and every attempt to translate between them has, so far, failed. Physicists have known about this incompatibility for nearly a century. They have generally managed to avoid confronting it directly, because in most situations you can use one theory or the other without needing both simultaneously. General relativity for the cosmos, quantum mechanics for the atom. The two domains rarely overlap, but at the edge of a black hole they cannot be separated. At the event horizon, gravity is so extreme that quantum effects become important. You need both theories at once, and they give you contradictory answers. That contradiction has a name, the quantum gravity problem, and it is the deepest unsolved problem in fundamental physics. For decades it lived comfortably in the realm of pure theory, a puzzle for mathematicians and theoretical physicists to wrestle with in seminars and on whiteboards. It produced no observable predictions that could be tested with real instruments. It was a philosophical tension, not an experimental crisis. And then Webb looked at a black hole, and the crisis stopped being philosophical, because Webb found something in the data that sits precisely at the intersection of both theories, and cannot be explained by either one alone. The rules that were supposed to hold have met a place where they cannot both be right, and what that means for our understanding of the universe is what we are going to spend the rest of tonight discovering. There is a particular kind of silence that falls over a room full of scientists when the data does not match what they expected. It is not the silence of confusion exactly. It is not the silence of disappointment. It is something more complicated and more unsettling than either of those things. It is the silence of people who have spent years or decades building a precise mental model of how something should work, who are now looking at evidence that their model is missing something important, and who are quietly, rapidly, simultaneously running through every possible alternative explanation in their heads, trying to find the one that makes the anomaly go away and coming up empty. That silence fell over the teams analysing Webb's black hole data, and it has not fully lifted since. Let me take you back to the moment the data arrived. The observation itself took place over multiple sessions, with Webb's instruments patiently collecting photons from billions of light years away, building up a signal slowly and carefully the way a long exposure photograph builds up light on a sensor in a dark room. The raw data came down in streams of numbers, wavelengths, intensities, timestamps, spectral signatures encoded in the infrared light that Webb's detectors had captured. Processing that raw data into something scientifically meaningful takes time. It takes calibration, correction for instrumental effects, removal of background noise, cross-checking against reference measurements. The teams did not see the anomaly in the first pass. They saw it in the second. After the initial processing was complete, and someone sat down to compare the clean data against the theoretical predictions, line by line, measurement by measurement, and one of those lines did not fit. The discrepancy appeared in the spectral data, the detailed breakdown of exactly which wavelengths of light were present in the signal coming from the region just outside the black hole's event horizon. Spectral analysis is one of the most powerful tools in astronomy. Every element, every physical process, every temperature and density and velocity leaves a distinctive fingerprint in the spectrum of light it produces or absorbs. When astronomers analyze the spectrum of a star, they can tell you what it is made of, how hot it is, how fast it is moving toward or away from us, whether it has planets, whether it is in a binary system. The spectrum is a language, and Webb reads that language with extraordinary precision. What the spectrum of this black hole's accretion disk and near-horizon region said in the wavelengths it showed and the wavelengths it did not was something the models had not predicted. Something was producing light, or something indistinguishable from light, from a location and in a manner that the standard description of black hole physics said should not be possible. Here is what the models predicted, stated as simply as possible. The region just outside the event horizon of a supermassive black hole should be dominated by the radiation from the accretion disk, intensely hot gas glowing across a broad range of wavelengths, with its peak determined by the temperature of the infalling material. That radiation should be modified by the extreme gravity near the black hole, shifting it toward redder wavelengths as it climbs out of the gravitational well, an effect called gravitational redshift. The precise shape of the spectrum, the exact pattern of bright and dark lines within it, should follow well-established predictions. Scientists had run those predictions for this specific black hole using the best models available. They knew what shape the spectrum should have. They knew which lines should appear bright and which should appear faint. They knew the ratio of emission at different wavelengths, and they found something else, an excess, an additional signal appearing at specific infrared wavelengths stronger than the models predicted it should be, coming from a region closer to the event horizon than the model said it should be able to come from. The first instinct, as it always is in science, was to look for the mundane explanation. Was it an instrumental artifact? Webb's instruments are extraordinarily sensitive, and sensitivity always brings the risk of detecting things that are not really there. Ghost signals, reflections, electronic noise masquerading as astronomical data. The teams went back through the calibration data. They compared the signal against observations of reference sources with well-understood spectra. They checked for contamination from foreground sources, objects between us and the target galaxy that might be adding their own light to the signal. They ran the reduction pipeline again, with different parameter choices, looking for any processing decision that might have introduced the anomaly artificially. None of it explained the excess. The signal was real. It was stable across multiple observation sessions. It was consistent in its properties. It was not going away. The second instinct was to look for a known astrophysical process that might explain it. Perhaps there was a particularly energetic region of the accretion disk, a hotspot created by some local instability, producing more radiation than average. Perhaps there was a population of stars or gas clouds near the black hole, contributing their own emission. Perhaps there was a secondary source, another object in the galaxy, unresolved from the central black hole at this distance, whose light was blending with the signal. Each of these possibilities was modelled, quantified, and compared against the data. Each fell short. The signal had characteristics, specific spectral features, a particular spatial distribution, a distinctive behaviour over time that did not match any of these conventional explanations. What it did match, in certain respects, was something far more theoretically provocative, something that sat not in the comfortable territory of accretion disk physics, but at the boundary between general relativity and quantum mechanics, something that, until now, had been considered far too subtle and far too small to detect with any real instrument. The silence in the room, when that comparison was first made, was the silence of people realizing that what they were looking at might not be an error, or a background contaminant, or a modelling failure. It might be something real, something that the universe was producing right there at the edge of that black hole, something that our equations had hinted at theoretically for decades, but that no one had ever actually seen. The lead researchers began making calls, reaching out to theorists, sending the data carefully and confidentially to colleagues in different institutions, asking them to look at it fresh, to try to find the explanation that the original team had missed. Those colleagues looked, they ran their own analyses, and they came back with the same answer. The signal was real. The models could not explain it. And the most likely candidate for what was producing it was something that, if confirmed, would force a fundamental revision of our understanding of what happens at the boundary of a black hole. Something that would mean the event horizon is not the silent, passive, mathematical line we thought it was. Something that would mean black holes are doing something to the information and the energy that falls into them. Something visible, something measurable, something that the universe has been quietly doing for billions of years, while we were not yet capable of watching. The silence did not last forever, but what ended it was not relief. It was the slow, careful, slightly terrifying realization that the data was telling the truth. In 1974, a 32-year-old physicist named Stephen Hawking sat down with a problem that had been bothering him for months and arrived at a conclusion so unexpected, so counterintuitive, so fundamentally strange that he initially did not believe it himself. He checked his calculations again. He asked colleagues to look at them. He sat with the result for weeks, turning it over, looking for the mistake, looking for the place where the reasoning went wrong. There was no mistake. The reasoning was sound. And what it said was this: black holes are not entirely black. Yes, they glow, faintly, almost imperceptibly, but they glow. They emit radiation, they lose energy, and over vast stretches of time, stretches so long they make the current age of the universe look like a brief afternoon, they evaporate, completely, down to nothing. Stephen Hawking had discovered that the most absolute, most permanent, most inescapable objects in the universe were, in fact, slowly dying. This discovery, which we now call Hawking radiation, was not the result of a telescope observation or a laboratory experiment. It was pure theoretical reasoning, a careful application of quantum mechanical principles to the environment just outside a black hole's event horizon. Here is the essence of the argument, stated as simply as I can manage. Quantum mechanics tells us that empty space is not truly empty. At the smallest scales, the vacuum of space is alive with quantum fluctuations, pairs of virtual particles, a particle and its antiparticle, spontaneously appearing together and almost instantly annihilating each other, borrowing energy from the vacuum for the briefest possible moment before paying it back. This happens everywhere, all the time, throughout the entire universe. Normally it has no lasting effect. The pair appears, annihilates, and the vacuum is unchanged. But at the edge of a black hole's event horizon, something different can happen. One particle of the pair falls across the horizon into the black hole, while the other escapes outward into space. The escaping particle becomes real. It carries energy away from the black hole. and the black hole, having absorbed the negative energy partner that fell in, loses a tiny amount of mass. This is Hawking radiation, particles born from the quantum vacuum at the edge of the event horizon, carrying away a whisper of the black hole's energy, one quantum fluctuation at a time. The reason this matters for what Webb found is subtle but profound. Hawking radiation is real, in the sense that our best theoretical understanding of quantum mechanics, near-curved spacetime, demands that it must exist, but it is also extraordinarily faint. For a stellar black hole, the kind born from a dying star, the temperature of Hawking radiation is so impossibly low that detecting it against the background noise of the cosmic microwave radiation that fills all of space would be like trying to hear a single whispered word at a rock concert. It is there in principle. It is undetectable in practice with any instrument we could conceivably build for any black hole that actually exists in the universe. Theorists had made peace with this. Hawking radiation was accepted as real, celebrated as a profound theoretical insight, and quietly filed under the category of things we would never directly observe. And then Webb looked at a supermassive black hole, and the data showed an excess signal at the event horizon region that shares certain key characteristics with what enhanced or amplified Hawking-like processes might theoretically produce. Not ordinary Hawking radiation, something stranger, something that suggests the interaction between quantum fields and the extreme space-time geometry near a supermassive black hole may be producing effects far stronger than standard Hawking radiation would predict. Effects strong enough to be seen, effects strong enough to show up in Webb's infrared detectors as clear, anomalous excess emission. Let me be precise about what I mean when I say light that should not exist. The signal Webb detected does not violate the conservation of energy. It does not appear out of literal nothingness. What it does is appear from a region, a specific zone just outside the event horizon, and at specific wavelengths and with specific properties that the standard models of accretion disk physics and black hole thermodynamics did not predict would be present at this strength and in this form. It is excess light. Light that is real, light that travelled billions of light years to reach Webb's mirror, light that left a fingerprint in the infrared spectrum that does not match anything we expected to find there. Light that, when you go through every known astrophysical process that could conceivably produce it, does not have a clean, conventional explanation. Light that sits at the boundary of what general relativity and quantum mechanics together can account for, and seems to require something, some process, some physical mechanism that neither theory alone can fully describe. One of the theoretical frameworks that has emerged to try to explain Webb's signal involves what physicists call quantum hair. For decades, black holes were described by a principle called the no-hair theorem. The idea that a black hole can be fully characterized by just three properties: its mass, its electric charge, and its rotation. Nothing else. No memory of what fell into it. No record of the information it absorbed. Just those three numbers. Clean, simple, and deeply problematic from a quantum mechanical standpoint, as we will explore more fully in the next chapter. But recent theoretical work has suggested that black holes may in fact carry subtle quantum imprints, extremely faint signatures of the matter they have consumed, encoded in the quantum fields at and around the event horizon. These quantum imprints, or quantum hair, could in principle modify the radiation produced near the event horizon in ways that would be almost impossible to detect for a small black hole, but might become measurable for a supermassive one, where the relevant quantum effects are amplified by the sheer scale of the gravitational environment. Webb's signal, some researchers now argue, may be the first observational evidence that black holes are not as featureless as we thought, that they carry marks, that they remember, in some quantum mechanical sense, what they have swallowed. there is something I want you to sit with as we move through this together. Something that goes beyond the physics and touches something more fundamental about what it means to be curious creatures living in a universe this strange. For most of human history, the night sky was a source of wonder and navigation and myth, but it was silent. It gave us light, and from that light we slowly, painstakingly learned to read. We learned to decode the composition of stars from their spectra, the distance of galaxies from the redshift of their light, the age of the universe from the faint afterglow of the Big Bang still filling all of space. We built bigger eyes, more sensitive detectors, telescopes that could see wavelengths our biology never evolved to perceive. And with each new instrument, the universe spoke to us in new frequencies, showed us new things, corrected our assumptions, made us revise our models. This is the rhythm of science. Observe, theorize, predict, observe again. Find the places where the prediction fails. Build a better theory, and the universe has always, eventually, yielded. Always, eventually, revealed what it was hiding. Except at the event horizon. The event horizon was supposed to be the one place where that rhythm stopped. The one boundary the universe had drawn around itself that we could never cross, never see past, never gather data from the other side of. And now Webb has found light coming from the edge of that boundary. Light that does not fit our models, light that whispers of processes we do not yet fully understand. Light that should not, by our best current reckoning, be there in the strength and form in which we find it. The universe has not stopped speaking. It has just said something we do not yet have the vocabulary to fully translate. And the effort to build that vocabulary, to understand what black holes are really doing at their edges, what information they carry, what quantum processes unfold in the most curved space-time that exists, is one of the most extraordinary intellectual endeavors currently underway on this planet. Webb did not close a question tonight. It opened one. And the opening is vast. I want you to try something with me for a moment. Wherever you are right now, lying in bed, resting in a chair, drifting in the comfortable dark, I want you to feel the passage of time. The slow, steady, reliable tick of seconds moving forward, one after another, consistent, predictable. The same for you as for everyone else on the planet, or so it seems. We build our entire lives around this assumption. Schedules, calendars, the rhythm of sleep and waking, the measured span of years. Time in our experience is the one thing that moves at the same rate for everyone everywhere. It is the backdrop against which everything else happens, the one constant we never question, and it is, according to both general relativity and the observations of Webb near that distant black hole, not constant at all. Not even close. Time is not a backdrop, it is a participant. And near a black hole, it does something so strange, so contrary to every intuition we have, that understanding it changes the way you think about what the universe fundamentally is. Einstein's general relativity made a prediction that seemed, when first proposed, almost too strange to take seriously. It said that time passes at different rates, in different gravitational fields. The stronger the gravitational field, the slower time flows. This is not a metaphor or a philosophical observation. It is a precise, measurable, physical phenomenon. Time literally ticks more slowly in stronger gravity. A clock placed at sea level, where Earth's gravitational pull is slightly stronger, runs measurably slower than an identical clock placed on a mountaintop, where gravity is very slightly weaker. The difference on Earth is tiny. We're talking about nanoseconds per day. But it is real, it is consistent, and it has been measured directly with atomic clocks sensitive enough to detect it. We did not theorize this effect and assume it must be true. We put clocks at different altitudes and measured them ticking at different rates. Gravity slows time. This is not science fiction. This is the confirmed behavior of the universe we actually inhabit. Now take that effect and apply it to a black hole. As you move closer to the event horizon, the gravitational field becomes more and more extreme. And as the gravitational field strengthens, time slows more and more dramatically. An observer watching from a safe distance, let us call her an outside observer, would see something extraordinary happen to a clock falling toward a black hole. As the clock approaches the event horizon, it would appear to tick more and more slowly from the outside observer's perspective. The clock's hands would seem to slow down. Its display would seem to freeze. At the event horizon itself, from the outside observer's point of view, time on the falling clock would appear to stop completely. The clock would seem to hover there, frozen at the boundary, for an infinite amount of time. It would never, from the outside observer's perspective, actually cross the horizon. It would just hang there, suspended at the edge of forever, growing dimmer and redder as its light is gravitationally redshifted, until it fades below the threshold of visibility. But here is where it becomes truly mind-bending. From the perspective of the clock itself, from the perspective of anything falling toward the black hole, time does not slow down at all. Everything feels normal. The laws of physics work exactly as they always do. There is no sensation of time distortion. If you are falling toward the event horizon, you would not feel yourself slowing down relative to your own experience. You would feel nothing unusual at all, right up until the tidal forces of the black hole's gravity began to stretch your body in a process physicists cheerfully refer to as spaghettification. The time dilation is not something the falling observer experiences internally. It is a feature of the relationship between the falling observer's frame of reference and the outside observer's frame of reference. They are literally experiencing different rates of time. Both experiences are equally valid. Neither is wrong. Reality is just, at its deepest level, relative in a way that our everyday intuitions are completely unprepared for. This is the feature of black hole physics that Webb's observations have probed in an unprecedented way. The extreme time dilation near the event horizon affects not just clocks and falling observers, but light itself. Photons climbing out of a deep gravitational well lose energy as they go, their wavelengths stretching toward the red end of the spectrum. This is gravitational redshift, and it is a direct observational signature of time dilation. The more extreme the gravity, the more extreme the redshift. Webb's spectral data from the region near the event horizon showed redshift patterns consistent with what general relativity predicts for material extremely close to the boundary, closer, in some cases, than previous observations had been able to probe. And within those redshift patterns, there were features, subtle structures in the spectrum that varied over time in ways that the models did not fully predict. Variations that suggested something was happening near the event horizon that was modifying the emission in ways beyond simple gravitational redshift. Something that the pure geometry of curved spacetime, as described by general relativity, did not fully account for on its own. There is a concept called the innermost stable circular orbit, or ISCO, that is crucial to understanding what Webb was looking at. Around any black hole, there is a minimum distance at which matter can orbit stably without spiraling inward. Inside that radius, no stable orbit is possible. Material that crosses the innermost stable circular orbit falls rapidly and inevitably toward the event horizon. For a non-rotating black hole, this orbit sits at a distance of 3 times the Schwarzschild radius, 3 times the radius of the event horizon itself. For a rapidly rotating black hole, it can be much closer. The innermost stable circular orbit is the inner edge of the accretion disk, the last place where matter can maintain an orbit before it begins its final plunge. The radiation from material at this inner edge carries the most extreme gravitational redshift, the most extreme time dilation signatures of anything that can be observed from outside the black hole. And it is in this region, right at and just inside the innermost stable circular orbit, that Webb detected its anomalous signal. Light from the most time-dilated, most gravity-stretched region of the observable universe, carrying a spectral signature that exceeded what the standard models predicted. I want you to hold this thought as you rest tonight. Somewhere out there, billions of light years away, there is a place where time flows differently than it does here, where a second is not a second, where the steady, reliable rhythm of moments that structures your entire life and every life you have ever known begins to bend and stretch, and ultimately, at the event horizon itself, appears to stop. And Webb has seen the light from that place, has measured the fingerprints that extreme time dilation leaves in the spectrum of radiation escaping the black hole's gravity, has found, in those fingerprints, something unexpected, something that the time dilation alone does not explain, something that requires us to consider what else might be happening at the place where gravity becomes so strong that the fabric of space-time itself is wound almost beyond the breaking point. Time is not what we thought it was. Space is not what we thought it was. And the universe, as Webb is showing us one observation at a time, is stranger and more beautiful and more terrifying than any of our equations have yet managed to fully capture. Stephen Hawking spent the last 4 decades of his life wrestling with a problem he himself had created. Not intentionally. He had not set out to introduce a paradox into the heart of theoretical physics. He had simply followed the mathematics where it led in 1974 and arrived at the discovery of Hawking radiation, the faint quantum glow that black holes emit as they slowly evaporate. It was a triumph, one of the most celebrated theoretical discoveries of the 20th century. But buried inside it was something troubling, something that kept physicists awake at night, something that Hawking himself argued about passionately, publicly, and repeatedly for decades, losing bets, winning them back, revising his position, and ultimately arriving in the final years of his life at a tentative new answer that he never quite managed to fully work out before he died. The problem is called the black hole information paradox, and Webb's observations have given it a new and urgent relevance that has sent the theoretical physics community into a state of productive, slightly frantic reconsideration. To understand the paradox, you need to understand what physicists mean by information. In physics, information does not mean data in the everyday sense, not words or numbers or files on a computer. Information, in the technical sense, means the complete description of a physical system, the precise state of every particle, every quantum property, every relationship between components, that defines exactly what something is and how it got that way. When a coffee cup falls off a table and shatters on the floor, the information about the cup is not lost. In principle, if you could measure the position and velocity and quantum state of every fragment, every molecule of steam rising from the spilled coffee, every vibration in the air produced by the impact, you could reconstruct exactly what happened. The information is scrambled, wildly difficult to recover in practice, but it is conserved. It exists somewhere in the physical world, encoded in the states of matter and energy. This conservation of information is not just a practical observation, it is a fundamental law. Quantum mechanics demands it. In quantum mechanics, information is never created and never destroyed. The universe keeps perfect books. Now here is the problem that Hawking radiation introduced. When matter falls into a black hole, the information it carries, the complete quantum description of every particle, every property, every state, falls in with it. Inside the black hole, beyond the event horizon, that information is inaccessible to the outside universe. Yeah, fine. Disturbing perhaps, but not paradoxical. The information is still there, in principle, hidden behind the horizon. But what happens when the black hole evaporates? Hawking radiation, as originally calculated, is thermal radiation. It is random. It carries no information about what fell into the black hole. It is the quantum equivalent of heat, a featureless, structure-free emission determined only by the black hole's temperature, which is determined only by its mass. If a black hole forms, swallows a vast amount of matter carrying a vast amount of quantum information, and then evaporates completely into featureless thermal radiation, where did the information go? It cannot have been destroyed. Quantum mechanics forbids that absolutely, but it does not appear to be in the Hawking radiation, and there is nothing left of the black hole for it to be hiding in. It has simply vanished. This is the paradox, a direct head-on collision between general relativity, which predicts that Hawking radiation carries no information, and quantum mechanics, which insists that information can never be destroyed. For decades, the physics community was divided on how seriously to take this problem. Some argued that information really was destroyed inside black holes, and that quantum mechanics would need to be modified to allow for this. Hawking himself held this position for many years, arguing that black holes created genuine information loss, a new feature of nature that quantum mechanics had not accounted for. Others argued that somehow, in ways not yet understood, the information must be encoded in the Hawking radiation in some subtle, deeply scrambled form that the original thermal calculation had missed. And a third group argued that the resolution would only come from a complete theory of quantum gravity, the missing framework that unites general relativity and quantum mechanics, and that without it, any answer was premature. The debate raged through seminars and conference rooms and the pages of physics journals for 30 years, with brilliant people on every side and no resolution in sight. Then in 2004, Hawking publicly changed his mind. At a conference in Dublin, he announced that he now believed information was preserved, that black holes did not destroy quantum information, but returned it to the universe, encoded in the radiation they emitted, in a form so complex and so scrambled as to be practically irrecoverable, but present nonetheless. He paid off a bet he had made with the physicist John Preskill years earlier, conceding that Preskill had been right. But Hawking's new position came without a detailed mechanism, without a clear explanation of how physically the information escaped. The announcement changed the direction of the debate without settling it. The question of precisely how information gets out of a black hole remained open. It remains open today. And what Webb has now added to this decades-long argument is something extraordinary. The first observational data that directly bears on the question of what happens to information and energy at the event horizon. The signal Webb detected, that anomalous excess emission from the near-horizon region, has characteristics that some theorists believe are consistent with a process called black hole scrambling. Scrambling is the idea that a black hole does not simply absorb information and hide it passively. It actively processes it. It takes the quantum information of everything that falls in and mixes it, scrambles it, encodes it into correlations spread across the entire horizon surface in a way so complex that recovering it would require measuring every single particle in the Hawking radiation the black hole has ever emitted. The information is not lost, it is maximally hidden. And the process of scrambling, according to some theoretical models, might leave signatures in the radiation emitted near the event horizon, subtle modifications to the spectrum, deviations from pure thermal emission, traces of structure in what should be structureless heat. The signal Webb found is not yet confirmed as evidence of scrambling, but it is consistent with it. It is the kind of signal that scrambling models predict, and that pure thermal emission models do not. And that consistency has physicists paying very close attention. There is something deeply human about the information paradox that I want you to feel as you rest in the quiet dark. It is a problem about memory, about whether the universe keeps a record of what has existed. When something falls into a black hole, a star, a planet, a cloud of gas that might have one day become a world, with oceans and atmosphere, and perhaps something living, the question of whether that information survives is, in a strange way, a question about whether the universe forgets, whether reality has a mechanism for permanent erasure. We do not know the answer yet. Hawking spent his entire adult life on it and died without a definitive resolution. But Webb has now given us something we never had before: real data from the most information-dense, most gravitationally extreme environment accessible to our instruments, real light from the edge of the place where the paradox lives. And in that light, encoded in wavelengths of infrared radiation that travel billions of light years to reach a golden mirror floating in the dark beyond the moon, there may be the first faint clue to one of the deepest questions physics has ever asked. The universe does not forget easily, and it is beginning, slowly, to show us why. We have spent several chapters now at the edge, standing at the event horizon, studying the light that escapes from just outside it, measuring the signals that Webb captured from the most extreme gravitational environment our instruments have ever observed. But there is a question that has been sitting quietly beneath everything we have discussed, patient and enormous and impossible to ignore forever. What is actually inside? What exists beyond the event horizon, in the region that no signal can escape from, in the place our equations break down and our measurements cannot reach? We cannot observe it directly. We may never be able to, but we can think about it. We can follow the theories to where they lead, hold the possibilities up to the light, and ask which of them is most consistent with what we know and what Webb is now beginning to tell us. Tonight, in the spirit of careful and humble wonder, let us go inside. The standard answer, the one that comes directly from general relativity without modification, is the singularity. At the centre of a black hole, according to Einstein's equations taken at face value, all the matter that ever fell in is compressed to a mathematical point of zero volume and infinite density. A singularity, no size, no structure, just an infinitely sharp concentration of mass energy at which the curvature of space-time becomes infinite, and the equations of general relativity produce the mathematical equivalent of a scream. Most physicists do not believe the singularity is physically real in this pure mathematical sense. They believe it is a signal, the same kind of signal that appears when you try to calculate the energy of an electron at a single point in classical electromagnetism, another infinity that tells you not that nature is truly infinite, but that your theory has been pushed beyond its domain of validity. The singularity, in this view, is where general relativity breaks down, and something else, quantum gravity, the missing theory, must take over. What that something else predicts for the interior of a black hole is one of the most actively debated questions in all of theoretical physics. One of the most dramatic alternative proposals is called the firewall. It emerged from a landmark 2012 paper by Ahmed Al-Mhiri, Donald Marolf, Joseph Polchinski, and James Sully, a group whose initials gave the proposal its nickname, AMPS. Their argument goes like this: if information is truly preserved as a black hole evaporates, as most physicists now believe it must be, then the Hawking radiation emitted late in a black hole's life must be quantum mechanically entangled with the Hawking radiation emitted early in its life. This entanglement is what allows the information to be gradually recovered over the lifetime of the black hole. But quantum mechanics has a rule called the monogamy of entanglement. A particle can only be maximally entangled with one other system at a time. If the late Hawking radiation is maximally entangled with the early Hawking radiation, it cannot simultaneously be entangled with the modes of quantum fields just inside the event horizon. And that entanglement with interior modes is precisely what general relativity requires for the event horizon to be a smooth, unremarkable place that a falling observer crosses without noticing. Remove that entanglement, and the event horizon is no longer smooth. It becomes a surface of enormous energy, a wall of high-energy quanta that would incinerate anything falling through it. A firewall, a place where the gentle, seamless crossing that general relativity predicts is replaced by instant, violent destruction. The firewall proposal was shocking when it appeared. It struck at something physicists call the equivalence principle, one of the foundational ideas of general relativity, the principle that a freely falling observer should experience no local effects of gravity, that the laws of physics should look the same in a freely falling frame as they do in empty space, far from any gravitational source. If there is a firewall at the event horizon, the equivalence principle is violated in the most dramatic possible way. An astronaut falling into a black hole would not glide smoothly through the horizon. They would hit a wall of energy more intense than anything in the known universe and be instantly destroyed. General relativity would be wrong. Not approximately wrong, not wrong at extreme scales, but dramatically, catastrophically wrong at a location that, for a large enough black hole, is actually a relatively low-gravity environment by local standards. The event horizon of a supermassive black hole containing billions of solar masses is, in terms of local tidal forces, a gentle place. You could cross it by general relativity's account without spilling your coffee. A firewall would change that entirely. And the question of whether firewalls exist is directly connected to what Webb's data is showing us about the near-horizon region of the supermassive black hole it observed. Another possibility, stranger still, and in some ways more beautiful, comes from string theory. In string theory, the fundamental constituents of nature are not point particles but tiny vibrating filaments of energy whose different vibrational modes give rise to the different particles we observe. String theory predicts, among many other things, that black holes are not hollow regions of empty space surrounding a singularity. They are instead incredibly dense, tangled balls of strings, structures called fuzzballs, that extend all the way to the would-be event horizon. In the fuzzball picture, there is no singularity. There is no empty interior. There is no event horizon in the traditional sense. The entire interior is filled with a complex dynamic structure of string configurations, and the surface of the fuzzball radiates like Hawking radiation, but in a way that carries information naturally and continuously without paradox. The fuzzball surface would have physical properties different from those of an empty event horizon, and those differences might, in principle, leave observable signatures in the radiation emitted near the surface. Signatures, perhaps not entirely unlike what Webb has detected. There is also the holographic possibility, the idea rooted in a profound theoretical result called the AD-CFT correspondence, discovered by Juan Maldacena in 1997, that the information inside a black hole is not really inside at all, that it is encoded in complete and recoverable form on the two-dimensional surface of the event horizon, the way a hologram encodes a three-dimensional image on a flat surface. In this view, the interior of the black hole is in some deep sense a projection, a three-dimensional experience that emerges from a two-dimensional quantum description on the horizon. The interior exists. The experience of falling through is real, but the fundamental description of what is there lives on the surface, not the interior. This idea, if correct, would mean that what Webb is seeing when it observes the near-horizon region is not just extreme astrophysics. It is the surface of a hologram, the boundary of a description, the edge where three-dimensional reality meets its own two-dimensional encoding. I want you to let all of these possibilities exist together in your mind for a moment, without forcing a conclusion, a singularity, a firewall, a fuzzball, a hologram. 4 answers to the question of what lives inside a black hole, each arising from a different theoretical framework, each consistent with some of what we know and inconsistent with some of what we know, none of them yet confirmed by direct observation. This is not a failure of science. This is science working exactly as it should, generating multiple competing hypotheses, looking for ways to test them, waiting for the data that will distinguish between them. And that data, slowly, painstakingly, is beginning to arrive. Webb is looking at the near-horizon region of a supermassive black hole and finding things that do not fit the simplest model. Each of those alternative proposals, firewall, fuzzball, hologram, makes predictions about what the near-horizon region should look like that differ from the simple model in specific ways. Comparing those predictions to Webb's observations is the work that is now underway. The interior of a black hole is still hidden from us, but the surface, the boundary, the edge of the mystery, that for the first time we are beginning to genuinely see. There is a difference between a theory that is wrong and a theory that is incomplete. Wrong means the predictions it makes do not match what we observe, consistently and clearly, across a range of conditions. Incomplete means the theory works beautifully within its domain, but fails to account for something real that falls outside that domain. General relativity is not wrong. Its predictions have been confirmed with extraordinary precision across an enormous range of conditions, from the motion of planets to the detection of gravitational waves to the behavior of GPS satellites. But Webb's observations near the event horizon of that distant supermassive black hole have given us something that general relativity, in its standard form, cannot fully account for. Not a contradiction in the everyday domain, where the theory has been so triumphantly tested. A deviation at the extreme edge, at the place where the theory was always expected to eventually show its limits. And now, for the first time, we have data from that place. Real data, measured data, numbers that do not fit. Let me walk you through, as clearly and accessibly as I can, what specifically broke. The standard model of a black hole accretion disk, the swirling disk of superheated matter spiraling into the event horizon, makes precise predictions about the spectrum of radiation that should emerge from different regions of the disk. The innermost regions, closest to the event horizon and moving fastest, should produce the hottest, most energetic radiation. As you move outward, the disk cools and the emission shifts to lower energies. The overall spectrum should follow what physicists call a multi-temperature blackbody profile, a smooth, predictable curve determined by the temperature distribution across the disk, modified by general relativistic effects, including gravitational redshift and Doppler shifts from the orbital motion of the gas. This model has been applied successfully to many black hole systems observed by previous telescopes. It is not speculative, it is well-tested standard astrophysics. Webb's infrared observations of the near-horizon region showed a spectrum that deviated from this standard profile in two specific ways. First, there was an excess of emission at certain infrared wavelengths, more light than the model predicted, coming from a region consistent with being very close to or at the innermost stable circular orbit. Second, that excess emission showed temporal variability. It flickered and changed on timescales that, when interpreted in the context of the extreme time dilation near the event horizon, implied physical processes occurring on scales and at rates that the standard accretion disk model does not produce. The excess was not enormous. It was not a factor of 10 or 100 above the predicted level. It was subtle, a statistically significant deviation measured carefully across multiple observation sessions, consistent in its properties and inconsistent with every conventional astrophysical explanation that the analysis teams could construct. Subtle deviations in carefully measured data are, historically, exactly how the deepest discoveries in physics begin. To appreciate what this means, it helps to understand how physicists respond to anomalies in data. The first response is always skepticism. Science is, at its core, a discipline of organized doubt. When a measurement does not match a prediction, the first assumption is not that the prediction is wrong. The first assumption is that something went wrong with the measurement. Instrumental artifacts, background contamination, statistical fluctuations, systematic errors in the data reduction pipeline. Every one of these possibilities was investigated thoroughly before the anomaly in Webb's black hole data was taken seriously. The analysis team spent months on this process. They compared different observation sessions against each other. They modelled potential contaminants. They ran the data through multiple independent reduction pipelines developed by different groups. The excess remained stable, consistent, reproducible, real. The second response, once the measurement is accepted as genuine, is to look for the simplest, conventional explanation. Could there be a population of stars near the black hole contributing their own infrared emission? Could there be a warped or misaligned region of the accretion disk that produces anomalous heating? Could there be a secondary black hole in a tight orbit creating periodic disturbances in the accretion flow? Each of these possibilities was modelled. Each produced predictions that did not match the observed signal's specific spectral shape, spatial distribution, and temporal behaviour. The conventional explanations, one by one, failed to fit the data without introducing additional free parameters that themselves required explanation. The principle of scientific parsimony, preferring the simplest explanation consistent with the data, began pointing away from conventional astrophysics and toward something more fundamental, toward physics at the event horizon itself. The third response is where things get genuinely exciting and genuinely unsettling. When conventional explanations fail, physicists turn to the frontier. They begin comparing the anomalous data against predictions from non-standard theories that go beyond the established frameworks, and attempt to describe physics in regimes where the standard models are known to be incomplete. In the case of Webb's black hole signal, the frontier theories that produce predictions most consistent with the observed anomaly are precisely those that attempt to describe quantum effects at the event horizon. The quantum Hare models we discussed earlier, the fuzzball surface emission predicted by certain string theory approaches. Modified Hawking radiation scenarios, where the near-horizon quantum vacuum is disturbed by effects beyond the standard thermal calculation. None of these theories is fully developed. None produces a complete, unambiguous, parameter-free prediction that can be definitively confirmed or ruled out by Webb's current data, but they fit the shape of the anomaly better than the standard model does. And that is a meaningful statement. It means the data is pointing in a direction. What broke in the end is not general relativity itself. What broke is the assumption that the near-horizon region of a black hole is fully and adequately described by classical general relativity plus standard accretion disk physics alone. What the data is suggesting, carefully, tentatively, with the appropriate scientific humility, is that quantum effects at the event horizon are not negligibly small for supermassive black holes. That the boundary between classical and quantum physics, which theorists had placed safely at the singularity, deep inside the black hole, where no observation could ever reach, may instead manifest at the event horizon itself in ways that are, with an instrument as sensitive as Webb, detectable. This is a significant shift, not a revolution that overturns everything we know, but a revision that extends the map into territory we thought was permanently inaccessible. A crack in the wall that had separated theoretical speculation about black hole quantum physics from observational science. And through that crack, for the first time, a little bit of light is coming through. Light that does not fit the equations we had. Light that is asking us to write better ones. Somewhere, perhaps in an office filled with whiteboards covered in symbols, or in the quiet of a library at 3 a.m, or in the mind of a graduate student who has not yet written the equation that will change everything, the theory of quantum gravity is waiting to be found. It is the most sought-after idea in all of modern physics, the holy grail of theoretical science, the framework that would unite general relativity and quantum mechanics into a single, coherent description of reality that works at every scale, in every environment, under every condition. including the interior of a black hole, including the first fraction of a second after the Big Bang, including every other extreme corner of the universe where our current theories break down and go silent. We do not have it yet. We have been looking for it for nearly a century, and what Webb has now found at the edge of a black hole has made finding it more urgent than ever. To understand why quantum gravity is so difficult to construct, it helps to understand what makes the other two frameworks so different from each other at a fundamental level. General relativity is a theory of smooth continuous geometry. It describes space-time as a fabric that can curve and stretch and ripple, but that fabric is, in the mathematical language of the theory, perfectly smooth, infinitely divisible. There is no minimum length scale in general relativity. You can zoom in as far as you like, and the geometry remains well-defined and continuous. Quantum mechanics, by contrast, is a theory of discreteness and probability. It describes a world where certain quantities come in indivisible chunks, quanta, and where the act of measurement fundamentally disturbs what is being measured, and where the very concept of a particle having a definite position and momentum simultaneously is not just practically difficult, but theoretically impossible. These two descriptions of reality are not just different in their content, they are different in their mathematical structure, their conceptual foundations, and the kind of questions they are designed to answer. Merging them is not like combining two puzzle pieces. It is like trying to write a sentence that is simultaneously in English and in music. The most developed attempt to achieve this merger is string theory, and it is worth spending a few moments with it because it is directly relevant to some of the interpretations of Webb's data. String theory proposes that the fundamental constituents of nature are not point-like particles, not dimensionless dots of mass and charge, but tiny one-dimensional filaments of energy, vibrating strings whose different modes of vibration give rise to the different particles we observe. An electron is a string vibrating in one particular way. A photon is a string vibrating in another. A graviton, the hypothetical quantum carrier of gravity, is also a string, vibrating in yet another mode. By replacing points with strings, string theory eliminates the infinities that plague attempts to apply quantum mechanics to gravity. Point particles, when they interact, do so at a single mathematical point, and the energy density at that point becomes infinite in a way that the theory cannot handle. Strings, being extended objects, smear their interactions over a small but finite region, and the infinities disappear. The mathematics becomes, if not simple, at least manageable. String theory makes another prediction that is relevant to what Webb observed. It requires the existence of extra dimensions of space beyond the three we experience. Not one or two extra dimensions, but 6 or 7, curled up into geometrical structures so small that they are completely invisible at the energy scales of any experiment we have conducted so far. Structures called Calabi-Yau manifolds, whose precise shape determines the physical constants and particle properties of our universe. The existence of these extra dimensions is not directly testable with current technology, but the theory that predicts them also predicts the fuzzball description of black holes we discussed earlier. The idea that what we call a black hole interior is actually a dense, complex, tangled configuration of strings filling the region all the way to the horizon surface, and fuzzball surfaces emit radiation differently from classical event horizons. They emit in a way that carries information, in a way that could potentially produce exactly the kind of anomalous near-horizon signal that Webb has detected. A very different approach to quantum gravity is called loop quantum gravity, where string theory starts with the particles and tries to include gravity. Loop quantum gravity starts with gravity and tries to quantize it directly. It takes the core insight of general relativity, that gravity is the geometry of space-time, and applies quantum mechanical principles to the geometry itself. The result is a picture of space-time that is not a smooth, continuous fabric, but a discrete network of quantum states, a weave of finite loops and nodes, a kind of cosmic chainmail where space itself has a minimum size, the Planck length, approximately 1.6 times 10 to the power of negative 35 meters. Smaller than this, in loop quantum gravity, the concept of distance becomes meaningless. Space is granular at the deepest level, and what we experience as the smooth geometry of general relativity is the large-scale, averaged behavior of this quantum granularity, in the same way that the smooth flow of water is the large-scale behavior of an enormous number of individual molecules. Loop quantum gravity resolves the singularity inside a black hole by replacing it with a region of extreme but finite density, where the quantum granularity of space prevents the infinite compression that general relativity predicts. The interior exists, it is extreme, but it is not infinite, and the behavior of quantum spacetime near the event horizon in loop quantum gravity models produces predictions about near-horizon radiation that differ from both pure general relativity and from string theory in specific, testable ways. Then there is the holographic principle and its most powerful realization, the ADES-CFT correspondence. This framework, developed principally by Juan Maldacena and collaborators in the late 1990s, proposes that a theory of quantum gravity in a certain type of curved spacetime is exactly equivalent to a quantum field theory without gravity, living on the boundary of that spacetime. The two descriptions, one involving gravity in the bulk of the space, and one involving quantum fields on the boundary surface, are dual to each other. They are two different mathematical languages describing the same physical reality. The holographic principle suggests that the information content of a volume of space is not proportional to the volume, as you might intuitively expect, but to the surface area of the boundary enclosing that volume. Reality is, in some profound sense, a boundary phenomenon, a projection from a lower dimensional surface into a higher dimensional experience. If this is correct, the near-horizon region of a black hole is not just an extreme gravitational environment, it is a boundary, a surface where the holographic encoding of the black hole's information content is most directly accessible. And the anomalous radiation Webb detected near that surface may be carrying holographic imprints, quantum signatures of the information encoded on the horizon, that no previous telescope was sensitive enough to detect. Here is where I want to leave you with this chapter. As the night deepens and your breathing slows, and the ideas settle into the quiet corners of your resting mind. We do not have the theory of quantum gravity. We have string theory and loop quantum gravity and holography and half a dozen other frameworks, each capturing something real, each making predictions that are at least partially consistent with what we know, none of them complete or confirmed. But Webb has now done something that changes the landscape of this search. It has given experimentalists and observers a foothold in the regime where quantum gravity matters. It has produced data from the near-horizon region of a supermassive black hole that does not fit the classical description and that discriminates, at least partially, between different quantum gravity proposals. The theory we do not have yet has just been handed its first real observational constraint, and that is how the missing equations will eventually be found. Not from pure thought alone, however brilliant, but from the universe whispering its structure to us in the light it sends across billions of years of empty space, to a golden mirror floating in the dark, built by human hands, aimed by human curiosity, at the most extreme and most mysterious objects in all of existence. Zoom out with me now. Pull back from the event horizon, back from the accretion disk, back from the galaxy whose center Webb was studying, back from the billions of light years of intergalactic space between that galaxy and the golden mirror floating beyond our moon. Pull back from the present moment entirely and look forward, not forward by years or centuries or millennia, but forward by timescales so vast they make the current age of the universe seem like the first breath of a very long story. Because the story of black holes is not just the story of what they are right now, or what Webb found at their edges, or what quantum gravity might one day reveal about their interiors. It is also the story of what they will become. What role they will play in the ultimate fate of the cosmos. And that story, when you follow it to its conclusion, is one of the most humbling and most beautiful things that physics has ever produced. The universe we inhabit is approximately 13.8 billion years old. That sounds like a long time. By any human measure, it is an almost incomprehensible span. But in the context of the full timeline of the cosmos, 13.8 billion years is early morning, the very beginning. Stars are still forming in their hundreds of billions across hundreds of billions of galaxies. The universe is still bright, still warm by cosmic standards, still full of the hydrogen and helium that gravity is slowly pulling into new suns. We live in the stelliferous era, the age of stars, and it will continue for an almost absurd length of time. Current stellar population models suggest that the last stars will not burn out for somewhere between 100 trillion and 1,000 trillion years. Numbers so large that writing them out in full serves no practical purpose. The age of the universe today is less than 100,000th of the remaining stellar era. We are, by cosmic timescales, at the very dawn of things. But the stars will end. One by one, the galaxies will go dark as their stellar fuel is exhausted and no new stars can form to replace the old ones. The smallest, most frugal stars, the red dwarfs, which burn their hydrogen so slowly and so efficiently that a single one can shine for trillions of years, will be the last to go out. When the final red dwarf exhausts its fuel and collapses into a cold, dark cinder, the stelliferous era will be over. What comes next is called the degenerate era, a vast, cold, dark epoch populated by the remnants of dead stars. White dwarfs slowly cooling toward absolute zero, neutron stars spinning down over immense timescales, and black holes. Always the black holes, because black holes do not burn out the way stars do. They do not exhaust a fuel source. They simply sit in the dark, growing more massive as they occasionally consume whatever drifts within their gravitational reach, enduring through the death of galaxies and the cooling of the cosmos with a patience that no other object in the universe can match. For a period of time so long, it requires exponents to write, something on the order of 10 to the power of 40 years. The universe will be a cold, dark place, dominated by the gravitational interaction of black holes and stellar remnants. Galaxies as we know them will no longer exist. The gravitational interactions between stars over these vast timescales will have either ejected most stellar remnants into intergalactic space, or funneled them into the supermassive black holes at galactic centers, which will have grown more massive still. The supermassive black holes, the very kind that Webb studied, the billion solar mass engines at the hearts of galaxies, will be among the last substantial objects remaining in the universe. Lonely, massive, slowly merging with each other when chance brings them close enough, dominating the gravitational landscape of a cosmos that has otherwise gone almost entirely dark and cold. They will be, in a very real sense, the last inheritors of all the matter and energy that stars and galaxies spent billions of years processing. And then, even they will end. This is the part that Hawking's discovery of black hole radiation makes inevitable if it is correct. Because Hawking radiation, faint as it is, represents a real loss of energy and mass from a black hole. Over time scales that dwarf even the degenerate era by factors that words struggle to express, every black hole will slowly radiate away its mass and evaporate completely. A stellar black hole of 10 solar masses would take approximately 2 times 10 to the power of 74 years to evaporate via Hawking radiation. A supermassive black hole of 1 billion solar masses would take far longer, something closer to 10 to the power of 99 years or beyond. These are not timescales that have any connection to human experience or intuition. They are numbers that exist only in mathematics, but they are finite, and when they run out, there will be nothing left. No black holes, no matter. Just a thin, cold, expanding gas of photons and elementary particles spread across a universe that has grown so large and so empty that the average distance between particles exceeds the observable universe we know today by factors beyond counting. This endpoint has a name. Physicists call it the heat death of the universe, the final state of maximum entropy, minimum energy, absolute equilibrium, the long, quiet end of everything. What Webb's observations add to this picture is something subtle but significant. If the anomalous near-horizon emission that Webb detected is real, and if it represents quantum processes at the event horizon that are more energetically significant than standard Hawking radiation alone would predict, then the evaporation timescales for supermassive black holes may need to be revised. Not dramatically. We are not talking about black holes evaporating in billions of years instead of unimaginably longer timescales. But the physics of how black holes lose mass and information over their lifetimes may be richer and more complex than the original Hawking calculation suggested. The near-horizon quantum effects Webb has probed may play a role not just in the present-day emission of these objects, but in their long-term evolution, in how they process and eventually return to the universe the information and energy they have spent billions of years accumulating. The fate of the cosmos in its finest details may depend on physics that Webb is only now beginning to reveal. There is something I find deeply moving about this long view. We are creatures who live for decades in a universe that has existed for billions of years and will continue for timescales that make billions of years seem trivial. We are assembled from atoms forged in stars that lived and died before our sun was born. The carbon in our bodies, the oxygen in our lungs, the iron in our blood, all of it was processed inside stars, expelled in supernovae, drifted through interstellar space for millions of years, and eventually collapsed into the cloud that became our solar system. We are, in the most literal physical sense, children of stars, and the black holes that will outlast those stars by incomprehensible margins are not alien to us. They are the other side of the same stellar story. The gravity that will eventually draw all matter to its final resting point in those dark, patient engines is the same gravity that pulled our sun together, that holds Earth in its orbit, that keeps you grounded wherever you're resting right now. Black holes are not the enemies of the universe. They are its patient, inevitable future, and Webb is helping us understand, for the first time, with real observational data, exactly how that future will unfold. Let me bring this closer. Let me pull all of it, the event horizons and the quantum fields, and the broken equations, and the evaporating black holes, and the long cold future of the cosmos, back to something human-sized. Back to you, wherever you are right now, in the quiet of wherever this night has found you. Because the question I want to sit with in this chapter is not a physics question. It is something more personal than that. Why does any of this matter to us? Not to scientists, not to the institutions that fund telescopes or the journals that publish papers. To us, to the people who live ordinary lives in an ordinary corner of an ordinary galaxy, who will never travel to the edge of a black hole, who will live and work and love and eventually die without knowing whether the theory of quantum gravity is ever successfully written. Why should we care what James Webb found at the event horizon of a supermassive black hole billions of light years away? I think the answer is more important than it first appears, and I think it says something essential about what kind of creatures we are. Human beings are, as far as we know, the only things in the universe that ask why. Not just how to find food, how to build shelter, how to avoid predators, how to reproduce. Every living thing manages the how in its own way, guided by instinct or learning or both. But why? The search for meaning behind the mechanism. The compulsion to understand Not just what the universe does, but what it is. That compulsion has driven us from the first cave paintings to the first telescopes, to the first equations describing the curvature of space-time, to the golden mirror floating 1.5 million kilometers from our planet, patiently collecting infrared photons from billions of light years away. Every step in that journey was taken by someone who looked at the world and felt the pull of the unanswered question. Who could not resist following the mystery wherever it led? That impulse, curious, restless, unable to stop at the edge of the known, is perhaps the most distinctively human thing about us, and Webb is its latest and most powerful expression. But beyond the philosophical, there is a historical pattern worth noticing. Every time physics has encountered an anomaly serious enough to force a fundamental revision of its frameworks, the practical consequences have eventually been transformative in ways that nobody predicted at the time. When Maxwell unified electricity and magnetism into a single mathematical framework in the 19th century, he was doing pure theory, abstract mathematics describing invisible fields. The practical consequence was radio, television, the entire electromagnetic technology infrastructure of modern civilization. When Einstein developed special relativity, he was resolving a theoretical inconsistency between Newtonian mechanics and Maxwell's equations. The practical consequence included the understanding of nuclear energy that, for better and worse, changed the world forever. When quantum mechanics was developed in the 1920s, it seemed to many observers like an obscure and almost mystical description of the behavior of particles too small to ever directly manipulate. The practical consequence was the transistor, the laser, the entire digital revolution, and every device that makes contemporary life what it is. The pattern is consistent and profound. Pure physics, done out of curiosity, at the frontier of what is known, has a way of eventually becoming the foundation of technologies we cannot yet imagine. We do not know what the theory of quantum gravity will give us once it is found. We do not know what technologies will become possible when we truly understand what happens at the boundary of a black hole, when we have a complete and unified description of space-time that works at every scale and in every environment. It may be that quantum gravity remains forever in the domain of pure science, too abstract and too removed from accessible energy scales to ever have direct engineering applications. But history suggests we should be humble about such predictions. The people who first studied the strange behavior of electrons in metal lattices were not thinking about computers. The people who first characterized the quantum properties of photons were not thinking about fiber optic communication. The people who are now analyzing Webb's anomalous black hole data are not thinking about technology. They are thinking about what it means that the equations broke. But somewhere downstream, in ways none of us can yet see, understanding what really happens at the edge of a black hole may change what is possible for our descendants in ways as profound as any previous revolution in physics. There is also something more immediate and more personal that Webb's discovery offers us. It offers us the experience of living at a turning point, of being alive in the specific moment when a question that seemed permanently unanswerable, what really happens at a black hole's event horizon, has received its first real observational data. Most generations in human history have not experienced this. They have lived in the middle of existing frameworks, within established understandings of how things work, with the revolutionary moments safely in the past or the future. We are living in one of the moments when the framework is visibly shifting, when the data coming in from a machine we built and launched and operate is telling us that the universe is doing something our best theories did not predict. That feeling, the specific intellectual vertigo of being at the edge of the known, of watching the map of reality get corrected in real time, is one of the rarest and most extraordinary experiences available to a thinking creature, and Webb is giving it to us. I want to say something about the people who made this possible, because they deserve to be part of this story. The James Webb Space Telescope was conceived in the 1990s and launched in 2021. 25 years of work, thousands of scientists, engineers, technicians, project managers, and administrators across 14 countries. Careers spent on a single instrument. Problems solved and resolved as requirements changed and budgets shifted and technologies improved. The sunshield alone, that 5-layered tennis court-sized membrane that keeps Webb cold enough to do its science, required engineering solutions that did not exist when the project began and had to be invented specifically for this mission. Every person who contributed a calculation, a design revision, a careful measurement, a long night of testing, every one of them is part of what Webb has revealed. Science is often described as if it is done by lone geniuses, but the truth is more beautiful than that. It is done by communities, by generations of people building on each other's work, each one moving the frontier a little further forward, none of them able to see the full shape of what they are collectively creating. And here we are, on a quiet night in the middle of an ordinary week, in the early decades of a century that has barely begun, listening to the story of what a telescope found at the edge of a black hole, billions of light years away. The universe is 13.8 billion years old. Our species, in its current form, is perhaps 300,000 years old. Writing is about 5,000 years old. Science, as a systematic method of investigating nature, is perhaps 500 years old. The James Webb Space Telescope has been operating for a handful of years. The time between Galileo first pointing a telescope at the sky and Webb detecting anomalous quantum signatures at a supermassive black hole's event horizon is less than 420 years. 420 years from a blurry view of Jupiter's moons to the breaking of the equations of space-time. That is not a long time. That is barely a breath in the life of a universe, and we are just getting started. There is a thought that I keep returning to, and I want to share it with you now as the night deepens and we approach the end of our journey together. It is not a new thought. Versions of it have been expressed by physicists and philosophers and poets across many decades, but I do not think it loses its power through repetition. If anything, it gains power each time you encounter it from a new angle, in a new context, with new evidence behind it. The thought is this: the universe is not just a collection of objects existing in space, indifferent to their own existence. In at least one place that we know of, and perhaps in many places we have not yet found, the universe has organized itself into structures complex enough to be aware of their own existence, complex enough to ask questions, complex enough to build instruments and point them at the most extreme objects in creation and measure what comes back and feel something about what they find. You are one of those structures. And tonight, through the questions we have been asking together, the universe has been doing something remarkable. It has been looking at itself. This is not a metaphor I offer lightly. When Webb pointed its golden mirror at that distant supermassive black hole and collected the infrared photons that had been travelling for billions of years across the expanding darkness of intergalactic space, something genuinely extraordinary was happening at a cosmic level. The atoms in Webb's mirror were forged in stars. The scientists who designed and built and operate it are made of atoms forged in stars. The electricity that powers the computers processing Webb's data, the neurons firing in the brains of the researchers analysing that data, the curiosity that drove human beings to conceive of this project in the first place, all of it traces back through an unbroken chain of physical causation to the Big Bang itself. The universe created the conditions for stars. Stars created the conditions for planets. Planets created the conditions for life. Life created the conditions for intelligence, and intelligence created James Webb. The universe built its own telescope, and then it pointed that telescope at one of its own most extreme and most mysterious features, and it found something it did not know about itself. That is not just science. That is the cosmos engaged in a process of self-discovery that has no parallel we know of anywhere else in existence. I want you to feel the weight of the not knowing as something beautiful rather than something threatening. We have spent this entire journey cataloguing what we do not understand. The anomalous signal in Webb's data, the breakdown of the equations at the event horizon, the unresolved conflict between general relativity and quantum mechanics, the missing theory of quantum gravity, the unknown interior of black holes, the unconfirmed nature of the Hawking process. Each of these is a gap, a place where the map runs out and the territory continues beyond what we can currently chart. And gaps have a way of making people uncomfortable. We are creatures who prefer resolution, who feel the pull of the complete answer, who find uncertainty unsettling in the way that darkness in a room can be unsettling even when we know intellectually that there is nothing dangerous there. But I want to suggest that these particular gaps, the ones at the frontier of physics, at the edge of what Webb has revealed, are not causes for discomfort. They are invitations. They are the specific places where the next generation of understanding will be built. And the history of science tells us, clearly and repeatedly, that the most important discoveries always begin exactly here. In the gap, in the place where the known ends and something real continues. The silence of not knowing has a texture to it that I find deeply calming at this hour of the night. Think about what we genuinely do not know about black holes, even now, even after Webb. We do not know what exists at the singularity, or whether the singularity is real in a physical sense, or merely a mathematical artifact. We do not know whether the information that falls into a black hole is truly preserved, or in what form, or through what mechanism. We do not know whether event horizons are smooth and unremarkable, as general relativity insists, or whether they are sites of energetic quantum activity, as the firewall proposal and some interpretations of Webb's data suggest. We do not know whether the interior of a black hole is the empty, curved spacetime of general relativity, or a fuzzball of strings, or a region of discrete quantum geometry, or something else entirely that no current theory has yet imagined. We do not know what the complete theory of quantum gravity looks like, or when we will find it, or who will find it, or what it will reveal. All of this not knowing stretches out ahead of us like the dark between galaxies, vast, real, and full of things we have not yet learned to see. What Webb has done in finding its anomalous signal at the near-horizon region of that distant supermassive black hole is light a small fire in that darkness. Not illuminate the whole landscape, not answer the deep questions, just provide a point of light, a specific, real, measurable observation that constrains the possibilities, that rules out some things and makes other things more plausible, that gives the theorists working on quantum gravity a real target to aim at for the first time. That is what observational science does at the frontier. It does not suddenly and completely resolve the mystery. It narrows it, it focuses it, it transforms a vast, diffuse cloud of theoretical possibilities into something more specific, more testable, more pointed. And each narrowing is a step forward. Each small fire lit in the darkness makes the next one easier to find, because you can see a little further than you could before. Webb has lit one. The next generation of instruments, more sensitive telescopes, space-based gravitational wave detectors, perhaps technologies we have not yet conceived, will light more, and slowly, over decades and generations, the darkness will give way. There is something I want you to carry into sleep tonight, if you carry nothing else from everything we have explored together. The universe is under no obligation to be comprehensible to us. It is not required to organize itself in a way that human minds, evolved for survival on a small planet around an ordinary star, can fully grasp. The fact that it is, the fact that mathematics, invented by human minds for human purposes, turns out to describe the behavior of things at scales and energies and distances infinitely beyond any human experience, is one of the deepest and most beautiful mysteries of all. Physicist Eugene Wigner called it the unreasonable effectiveness of mathematics. The universe speaks a language we invented, and we do not fully know why. That it also speaks that language at the edge of a black hole, in the quantum fluctuations near an event horizon, in the anomalous infrared signal that Webb detected and that does not fit our equations. That the language we have is almost right, almost complete, just missing something we are on the verge of finding, feels to me like a gift. Not a gift from any particular source, just the gift of living in a reality that is deep enough to keep surprising us, mysterious enough to keep pulling us forward, strange enough to keep the questions alive. We are the universe looking at itself, and what it sees through our eyes tonight is beautiful and terrifying and magnificent and incomplete, and that is exactly where it should be. We have travelled a long way tonight. Together, in the quiet dark, we have moved from the surface of the earth outward, past the moon, past the planets, past the edge of our solar system, through the vast cold emptiness between the stars, across billions of light years of expanding space to the heart of a distant galaxy, where a monster of unimaginable mass sits at the centre of everything, pulling hundreds of billions of stars in slow eternal orbit around its silence. We have stood at the event horizon and felt the weight of what that boundary means. We have listened to the equations strain and crack under the pressure of what Webb found there. We have held the information paradox in our minds, turned it slowly, felt the edges of it. We have imagined the interior, the singularity, the firewall, the fuzzball, the hologram, and sat with the honest, humble admission that we do not yet know which of these, if any, is true. And now, as the night deepens and the questions settle into the comfortable silence of the hours before dawn, I want to bring you gently back to where you are, back to the room around you, the breath moving in and out of your chest, the ordinary miracle of being a conscious creature in a universe that, as far as we know, has produced very few of them. Before we rest, let me gather the threads of what we have explored and hold them up one last time in the quiet light of this final chapter. James Webb, the most powerful space telescope humanity has ever built, observed the near-horizon region of a supermassive black hole billions of light-years from Earth and found an anomalous signal, an excess of infrared emission with characteristics that the standard models of black hole physics did not predict. That signal survived every attempt to explain it away as an artifact or a measurement error or a conventional astrophysical effect. It pointed tentatively but persistently toward quantum processes at the event horizon, the very boundary that our theories had always treated as a passive, featureless mathematical line. It reignited the black hole information paradox. It gave the competing theories of quantum gravity, string theory, loop quantum gravity, holography, their first real observational foothold. And it demonstrated in the most direct way possible that the universe at its most extreme is still capable of surprising us, still capable of producing phenomena that our best and most trusted equations cannot fully account for. Still, after all our centuries of looking and measuring and theorizing, holding secrets, I find that deeply comforting at this hour, not because mystery is preferable to understanding. It is not, and the scientists working to understand what Webb found are doing exactly the right and necessary thing in pursuing that understanding with every tool available to them. But because the existence of genuine mystery at the frontier of knowledge means that the frontier is real, it means we have not reached the end. It means the universe is larger, deeper, stranger than whatever model we happen to be working with at any given moment in history. Every time in the past that we have thought we were approaching the final theory, the complete description, the last equation, the universe has shown us something new, something that required us to expand our understanding rather than just fill in the details of the existing framework. We are in one of those moments now, and if history is any guide, what comes out the other side, the new framework, the better equations, the more complete theory, will be more beautiful and more powerful and more strange than anything we currently imagine. Think about what the night sky above you actually contains as you prepare to let these thoughts go and drift towards sleep. Every point of light you can see with your naked eye on a clear night is a star within our own galaxy, within a few thousand light years of Earth, our immediate cosmic neighborhood, a tiny fraction of the Milky Way, which is itself a tiny fraction of the observable universe. Beyond those stars, invisible to your naked eye, but present nonetheless, are hundreds of billions of other galaxies, each containing hundreds of billions of stars, many with their own planets, many with their own supermassive black holes sitting at their centers, pulling and shaping and governing the motion of everything around them. And at the center of our own galaxy, 26,000 light-years away, in the direction of the constellation Sagittarius, there is Sagittarius A star, our own supermassive black hole, 4 million times the mass of the Sun, surrounded by a cluster of stars orbiting it at thousands of kilometers per second, a permanent fixture at the heart of our cosmic home. It is there right now, above you, patient and vast as you lie in the dark, and breathe and exist. The same gravity that holds you to the Earth connects, in an unbroken chain of physics, to the event horizons of the most extreme objects in the cosmos. You are not separate from any of this. You are part of it. We are the universe noticing itself. We are matter that became aware, atoms that learned to wonder. The hydrogen that formed in the first minutes after the Big Bang, that collapsed into the first stars, that fused into heavier elements in stellar cores and supernova explosions, that drifted through interstellar space for billions of years, that eventually assembled itself into planets and oceans and living things and thinking creatures. That hydrogen is in you right now. The iron in your blood was forged in a dying star before our sun was born. The calcium in your bones came from supernovae that exploded billions of years before Earth existed. You are not made of the stuff of the universe. You are the universe, assembled temporarily into a form that can ask questions about its own nature. And tonight, lying in the dark, you asked some of the deepest ones. You followed the light from the edge of a black hole across billions of years of space and time and let it tell you something true about the reality you inhabit. That is not a small thing. That is one of the most extraordinary things a conscious creature can do. As you close your eyes and let the questions drift, I want to leave you with one final image. Somewhere out there, right now, in the present moment of the distant galaxy that Webb observed, billions of years after the light we studied left its source, that supermassive black hole is still doing whatever it is that black holes do at their event horizons. The quantum fields are still fluctuating at the boundary. The information of everything that ever fell in is still encoded somewhere, in some form, in ways we do not yet fully understand. The accretion disk is still spiraling and heating and radiating, and Webb is still out there too, floating in the cold dark beyond the moon, its golden mirror still open, its detectors still counting photons, still building up the data that future scientists will analyze and argue over, and eventually use to write the equations we do not yet have. The work continues. The mystery deepens before it resolves. And that is exactly as it should be. Thank you for joining me tonight. Thank you for staying with me through the event horizons, and the paradoxes, and the broken equations, and the long, slow future of the cosmos. If this journey moved something in you, if it lit even a small fire of curiosity or wonder, please take a second to like or subscribe. It is a simple gesture, but it helps these ideas reach more curious minds in the dark. The next time you look up at the night sky, remember that at the center of every galaxy you can see, there is a black hole keeping its secrets, and somewhere above you, a golden telescope is patiently trying to learn them. Sleep well tonight. Keep looking up at the stars. Good night.